A block of mass m slides down an inclined plane of height h that makes an angle theta with a horizontal. The block has an initial speed v1 at the top of the incline and reaches the final speed v2 at the bottom. Determine the coefficient of friction between the block and the surface of the incline. So for this type of conservation of energy question, the first thing you need to do is write down the equation of the conservation of energy. So first, let's analyze what type of energy exists when the block is at the top. The block is moving at an initial speed v1, right? So it definitely has the kinetic energy, and it is h above the ground. So gravitational potential energy exists. So let's write down mgh plus 1 half mv1 squared. This is the amount of energy it has when it's at its initial position. And when the block reaches the bottom, it only has a kinetic energy, right? Because it is not above the ground at all at this moment. So this much energy supposed to be equal to 1 half m times v2 squared. The reason why I said it's supposed to be equal to is that if there's no friction exist on the incline, these two will be equal. However, now the friction exists, so the friction will do work, right? And it will actually cancel out some of the energy during the entire process. So over here, we should write minus work done by the friction force. So how do we calculate the work done by the friction? Work done by the friction obviously is equal to friction force times the distance it travels. And FF over here is equal to the normal force times mu. Do you now see that everything actually comes together? Like when you originally see the question, it gives you V1, gives you V2, and you may think there's nothing that can actually relate it to the coefficient of friction, but actually it can. It's right here. So how do we solve the expression for the normal force? Let's just draw a free body diagram. This is Fn, this is Fg, and this is FF. And also, over here, you don't really need to put cosine theta here because the angle between the friction force and the direction that the object is moving is actually 0 degrees. And cosine 0 degrees is equal to 1, so we ignore it over here. And also, the block is not like moving straight up towards the surface or even break into the surface, right? So the object is at equilibrium in the direction vertically to, relative to the surface of the incline. So we can just write the components or write the net force equation out. This is theta. Net force y towards incline is equal to Fn minus Fg times cosine theta equals 0. So we can get Fn is equal to Fg cosine theta and it's equal to mg cosine theta. So now let's plug mg cosine theta back to the original function, which we can get the work done by the friction is actually equal to mg cosine theta times mu times d. Well, before we plug it back to the original function, we should simplify it to the version that we love to see. For example, we will put work done by the friction on one side and the other expressions on the other side. And then after we simplify, we'll get VF is equal to mgh plus 1/2 m times v1 squared minus v2 squared. And then let's plug this back here. So now it will be mg cosine theta times mu times d. D is the distance it travels along the incline. So this is h, right? Distance it travels, it would just be h over sine theta. And that's equal to mgh plus 1/2 v1 squared minus v2 squared. And then you can easily see that m can be cancelled well. And then let's move everything over here except for mu to the other side. So we divided them on both sides, which will get you the final answer. Oh, I forgot there's an m here. Which will get you the final answer. Mu is equal to tangent theta times v1 squared minus v2 squared over 2gh plus 1. And that is your final answer. There's a tangent h exists because cosine theta over sine theta is equal to cotangent theta, or 1 over tangent theta on the left side. So if you want the right side to get tangent theta, you multiply it by tangent theta. And then m can be cancelled out. Yep, I think that's correct.